بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome to chapter 19 of this textbook, which is talking about circuit theorems. In this chapter, first of all, I'm going to review with you the circuit laws, which was discussed mainly in Circuit 1 course. Then we will go again through the circuit theorems, but with the respect of AC circuits. First we will talk about superposition theorem, then Thevenin theorems, Norton theorems, which is clubbed together, then the maximum power transfer theorems. In this part of the lecture, I'll be focusing on the first and second outlines. So to review the circuit laws, I'm gonna go through a few slides. First of all, this is the Ohm's law, and which is relating the voltage, current, and resistance. So this is the Ohm's law, the most fundamental law in circuits. So in this law, the three main variables are interconnected and related. So the voltage, current, and resistance are related to each other in case of purely resistive load. But in the case of impedance, it will be impedance, voltage, current, which is related to each other. So as we can see from the first law here, V equal IR, but here we are changed to V equal I times Z. And whenever we're talking about impedance, you know it that we are talking about complex numbers instead of real numbers. Okay, the first part of these laws is talking about the voltage. So the Kirchhoff voltage law, which we call it normally KVL, is the algebraic summation of the voltages in closed loop path in circuits is equal to 0. So if you try to sum the voltages across this loop, the summation will be equal to 0. So Vs, in this case, if we start from here, it will be minus Vs plus V1 plus V2 plus V3 will be equal to 0. So this is basically the KVL. And now we're talking about complex numbers. Now, second part about series circuits, we should talk about the voltage divider. So if we want to find the voltage across any of these three elements or any elements in a series connection, we can use this voltage divider. So the voltage drop across a series impedance is directly proportional to its impedance. So the voltage here is proportional to the impedance here. And again, this is complex numbers. I don't need to repeat this again and again. If we move to the parallel circuit, we should talk about the Kirchhoff current law, KCL. So the algebraic summation of all currents into a node in a circuit is equal to 0. So the current in this node, the summation of all currents entering, exiting this node will be equal to 0. So this minus this minus this minus this will be equal to 0. Now, talking about the current, we have to come across the current divider rule. So in parallel circuits, the current through any parallel impedance is inversely proportional to the impedance. It is opposite, not similar to the previous one. So the current through any branch is inversely proportional. So the Z will be in the bottom, inversely proportional to the impedance. In the case of voltage divider rule, the VI will be in the top. In the case of current divider rule, the ZI will be at the top. In the case of the current divider rule, ZI will be in the bottom. And again, this is complex numbers. That's all. So this is the first part. We discussed the Ohm's law. We reviewed the Ohm's law. We reviewed the series circuits with two perspectives, the KVL as well as the voltage divider rule. Then we discussed the parallel circuits where we come across the KCL as well as current divider rule. With this introduction, we will be able to start the first section in this chapter, which is talking about the superposition theorems. So superposition theorems in DC circuits, as we've seen before, is really applicable to the AC circuits using complex numbers. So used for circuits in multiple sources to solve the variables at any element. So if we have multiple sources in the same circuits, we can use this theorem to find out the voltage, which is the variables, or the currents at any elements. Now, the theorems basically says the following. In a circuit with multiple sources, the current or the voltage in any element is nothing but algebraic sum of currents or voltages produced by each source acting alone. So basically they're telling to switch off all sources except one at a time and then calculate the portion of that source on that specific element. And repeat this again and again till you cover all the sources and then do the summation. Let's take an example to clarify this point. We've seen it in the DC, now we're going to see it in AC, and the main difference is that we're talking about complex numbers. For this example, now what is the current in C2? So now the question is about C2, and we want to calculate the current at this capacitance. Now the first step is to replace or to switch off all sources except one of them. So I picked this source and make it on and switch off all other sources. So this is the other sources and I switch it off, and meaning switching off with the voltage source, I have to replace it with a short circuit. So the first step, I have to draw this circuit when I switch off all other sources. Then, using this circuit, I have to analyze the circuit to find out what is the total impedance. So, if I want to find the total impedance, will be very clear that the C2 is in parallel with R, and this total will be in series with C1. And if I plug these numbers inside here, so R with C2 in parallel plus C1, and I put all the complex numbers, and you know all these operations has to be done. And finally I got this, which is the Cartesian representation, rectangular representation, as well as the polar representation of the total impedance. Now, after that, I have to find out using this what is the total current for the voltage source number 1. So this VS1 will be equal, the IS1 will be equal VS1 over Z. So the total impedance comes over here, and this is the VS. So if I want to find what is the current coming out from the VS, it will be VS divided by the total impedance. And if I plug these numbers, the VS is 5, and the Z total, as we have calculated from here, it is 13.5, and the angle is minus 63.2. And if we plug these numbers together in the calculator, we get this result. Then the point is not we're needing the total current, because the total current will pass through C1 only, but at this point it will divide, the current will be divided into two branches. So using the current divider rule, I can put the C2 at the bottom and put the total at the top. This is one alternative, and the other alternative is explained over here, where I use the R in the top and the total in the bottom, and times IS1, and the results will be exactly the same if you use any one of them. Then if you plug the numbers, you will get the IC2 portion of the voltage source number 1. So this is the first part. I have to calculate the variable from the voltage source number 1, the first source. Now I have to repeat this same exercise for the second voltage source. So doing so, first of all, I have to draw the circuit again, switch off VS1, switch on VS2, and then plug these numbers to find out what is the total impedance, and it will be C1 in parallel with R, all together in series with C2. So R with C1 divided by R plus C1, all this is in parallel, then it will be added to the series XC2. In fact, I have a comment over here where you should use ZC2 instead of XC2. So please correct this in your note. And then if you plug all these numbers, you will start manipulating these complex numbers till you get the results in rectangular form as well as in polar form. Then, fortunately, our current that we're looking for is the total current, indeed, in this case. So just simply I will write IS2 is equal to the total current, which is VS2 over total Z, and this will be our second portion of the current. Just keep in mind that the IS2 is in the opposite direction of IC2, and in that case we just have to flip the signs, or we add 180 degrees at the angle. So step number 3, I have to do the addition of both portions or component of the currents from both sources. Now switched on both sources, and here I will do the math to add both of these variables. So this is the polar representations. I have put it back into rectangular because I'm doing addition. Then this is another polar representation from second part. I just change it to this rectangular form. Then I will do a normal summation of both of them, and this will be the results. And if I want, I can change from rectangular form back to the polar form for the total, and will be our final results. In fact, this minus sign showing over here, if we look at minus 124, this will be in the third quadrant of the plane, imaginary complex plane. So this gives us an indication that the current is going into the opposite direction, because normally we prefer to have it from plus 90 to minus 90, and if it is more than that, then we prefer to switch off the sign and to give the minus direction to the right position. So in summary, to do a superposition theorem, what are the steps in it? First step is you have to leave on one source and zeroing all other sources. And meaning zeroing all other sources, you replace them by their internal impedance. For voltage sources, the internal impedance is 0. It is then you replace it with short circuit, and for current sources, the internal impedance is infinite, and then you replace it with open circuit. So the first step here, switch off all other sources. Voltage sources, put it a short circuit. Current sources, put it as an open circuit. Then second step, find the current in the branch of interest and produce one remaining source. So with that single source on, find the current. Third step, repeat the step number 1 and 2 again and again for each and every source you have in the circuit. So if you have 2 sources, you have to repeat this procedure twice. If you have 3 sources, you have to repeat it thrice, and so on. Number 4 and the last, add the individual currents or voltages values as phasor quantities, complex quantities, and find out what is the final value. That's it. Thank you for listening, and let's see you in the next part of this lecture.